Good afternoon to all. Myself, K. Manjula, Assistant Professor of Physics, Dr. BRR Government Degree College, Jadchalra, Mahabubnagar. In this today's class, let us try to understand the Joule Kelvin effect and what is the use of that Joule Kelvin effect. What are the features of this Joule Kelvin effect and derivation of Joule Kelvin coefficient and calculation of this Joule Kelvin coefficient for ideal gas and van der Waals gas. These are these things we are going to understand in this class. So, firstly, let us let us try to understand the concept of Joule Kelvin effect. What is Joule Kelvin effect? Here see, when a gas is subjected to pass through a porous plug. Here porous plug is nothing but a system which is having small tiny holes like cotton type material or the woolen type or silk type or fiber type, or it is better to imagine that is porous plug is nothing but a kerchief also, and daily we use that kerchief, that is kerchief and duster chalk, and we use chalk and duster behaves like a porous plug. So, when a gas is subjected to pass through this porous plug, it suffers a change in its temperature. Means, see here you are observing. Here you are observing this porous plug. Here in this slide you are observing this is porous plug. When the gas, this is a stream of gas is allowed to this porous plug, means it is passing from high pressure region to low pressure region. So when it is passes from high pressure region to low pressure region, it suffers a change in its temperature. This is known as a Joule Kelvin effect, or sometimes this is also known as a throttling process. Throttling means means the small tiny holes in this porous plug material behaves like a throttles. So for that purpose we call this Joule Kelvin effect as a throttling process. So this is the definition of the Joule Kelvin effect. See here in this figure, two thermometers are kept here, T1 and T2. T1 is the before passing the gas through the porous plug, and T2 is at the after passing the this porous plug. So when a gas enters from, when a gas passes through this porous plug from high pressure region to low pressure region, this passing out gas suffers some change in its temperature. So after understanding this Joule Kelvin effect, a question arises: what is the reason for change in its temperature? What mechanism is going on this throttling process or Joule Kelvin process? See here, for this when you see this porous plug or throttling system, when the gas enters into the throttling system, or when a gas enters into this porous plug, it has to move some distance, means it has to drag out, means it has to do some work. So that is the concept. A stream of gas enters into this throttle. After enters into this throttle or porous plug, it has to draw, it has to move some distance. So means it has to do some work. To do some work it needs some energy. From where that energy it gets? Here it is a adiabatic process. Same, this total Joule Kelvin effect, this porous plug is the adiabatic process. So to do this work, means why the gas has to do, because it has to move. So like that, so it has to do some work against to the intermolecular forces of attraction between the molecules. So for that purpose, to do that work, it takes its own internal energy, so that its internal energy decreases, so that its temperature decreases, means it internal energy changes, so that its temperature changes. This is the main concept. Due to the work done by the gas against to the intermolecular forces of attraction, the change in temperature arises. So this is the reason. So this the gas, while passing through the pores of the plug, gets long drawn. In the process of, the gas has to do work against the intermolecular attractive force. But here this expansion is under adiabatic conditions, so that the change in temperature of the gas, there is a change in temperature of the gas. This is the reason why the temperature of the gas changes in the Joule Kelvin effect. Next, after understanding the principle, next what is the use of this Joule Kelvin effect? This porous plug experiment gives the existence of the intermolecular forces of attraction. Due to the intermolecular forces, the gas is doing some work, so that there is arising a change in temperature. If there are no intermolecular forces, there will be no change in the temperature. But here the change in temperature is arising. So this is the main concept of the Joule Kelvin effect. Intermolecular forces of attraction will be present. Next, this by using this Joule Kelvin effect, liquefaction of air is also done in most economical way. Means by using this Joule Kelvin effect uses in getting the low temperatures of a systems. So after next in this porous plug or Joule Kelvin experiment, some observations are done. Next, change in temperature arises. Okay, this change in temperature depends upon what quantities. So that is the observations. Automatically, what we can understand, that the change in temperature is directly proportional to the pressure difference of the two sides of the plug, because our gas is going from constant high pressure region to constant low pressure region. If this difference is varies, the temperature also, change in temperature also varies. So the first observations in this porous plug experiment is that the change in temperature is directly proportional to the change in the pressure difference of the two sides of the plug. After that, another important thing is that as the initial temperature, if the initial temperature of the gas increases, means when the gas is entering into the porous plug, if then the initial temperature of the gas increases, the cooling effect decreases. So this is the main criteria. If the initial temperature is increases, that means cooling effect decreases. Another thing is that at a certain initial temperature, the cooling effect changes into heating effect. That temperature is known as an inversion temperature. At inversion temperature, what is the inversion? At the inversion temperature, there is no heating or there is no cooling. There is neither gas gets cooled, neither nor gas gets cooled. Similarly, naturally at ordinary temperatures, experiments reveals that at ordinary temperatures, all gases except only hydrogen and helium shows cooling effect. But only two gases, that is hydrogen and helium, show heating effect. Only these two, because the inversion temperature of these hydrogen and helium are minus 80 degrees centigrade and minus 240 degrees centigrade. These are very far from the room temperature. So that for this purpose, the gases show heating effect after throttling processes. So These are the observations are observed in the porous plug experiment. Mainly, this change in temperature depends upon the pressure difference of the two sides of the porous plug. After understanding these observations, let us try to define the derive the Joule Kelvin coefficient, because when all gases passes through this porous plug, they may get cooled, they may get heated. So the cooling or heating depends upon the pressure difference. So what is the that cooling cooling coefficient, like the JK coefficient we call it as a, for that purpose, when the gas is enters into the porous plug, what are the initial pressure and initial value? Let P1 and V1, these are the initial pressure and volume before passing. And similarly, we assume the pressure of the gas and volume of the gas after passing through this porous plug, say that is P2 and V2. So, the when this gas enters into this porous plug, and the work is done by the gas. How much work is done? That is P2 V2 minus P1 V1. This is the work done against to the intermolecular forces of attraction of the gas. Who is supplying some energy to do this work? That is, it takes from its internal energy, because there is a change in internal energy. Similarly, what is the change in internal energy? So, if U1 and U2 are the initial and final internal energies of the gas, or according to the according to the first law of thermodynamics, this change in internal energy must be equal to, that is, you are observing the change in internal energy, that is U1 minus U2, must be equal to what? The work done. So that is P2 V2 minus P1 V1. This is the main equation in this Joule Kelvin effect. That is U1 minus U2 is equal to P2 V2 minus P1 V1. On simplifying, we get U1 plus P1 V1 is equal to U2 plus P2 V2. By seeing this equation, we understand that AU plus PV is equal to constant. Even though there is a change in internal energy, but the term U plus PV is equal to constant. What is this U plus PV constant? That means, therefore, during throttling process, although there is a pressure difference on two sides of the porous plug, the total U plus PV will be constant. U plus PV is nothing but the enthalpy. Already we know that U plus PV is an energy function. This is known as a enthalpy. Enthalpy remains constant in the Joule Kelvin effect. So that i.e., that means H is equal to U plus PV is equal to constant. Let us calculate change in enthalpy. That is, differentiate this equation. That is complete differentiation. dH must be equal to du plus PdV plus VdP is equal to 0. But we know that du plus PdV, according to first law of thermodynamics, du plus PdV must be equal to dq, supplied energy, supplied heat. So, all again dq must be equal to, according to second law of thermodynamics, Tds, because we are converting the system into entropy terms. So for that purpose, just in this dH above equation, just substitute in place of du plus PdV Tds. So the equation becomes Tds plus VdP is equal to dH, because as H is equal to constant, the change in enthalpy also 0. So that means Tds plus VdP must be equal to 0. So say this is the first equation, because means what we are doing is, next slowly we are thinking about the entropy in the Joule Kelvin effect. Let this entropy is a function of pressure and the temperature. So that is S is a function of T and P. So complete differential in the entropy. S is a treated as a perfect differential. What is the value of ds? So ds can be written as ds is equal to dou s by dou t by keeping as a pressure as constant, dou s by dou t at constant p into dt. Similarly, by keeping temperature as a constant, though we can write dou s by dou p at constant t into dp. Say this is a second equation. By seeing this first and second equation, just substitute this ds value in the first equation. Then the equation changes t into d. In the place of ds, we are substituting second equation. That is t into dou s by dou t at constant p dt plus dou s by dou p at constant t dp plus as it is this vdp term is equal to 0. Say this is the third equation. In this third equation, let us think about this first term, that is t dou s by dou t at constant p. Dou s means tds. Tds is nothing but second law of thermodynamics. It gives the total heat supplied, that is dou q by dou t at constant p. Again, this heat supplied at constant pressure must be equal to specific heat at constant pressure. So this means totally T dou S by dou T at constant P can be written as Cp. Again, coming to the second term in the second equation, dou S by dou P at constant T can be written as, we are using Maxwell fourth equation here. Instead of dou S by dou P at constant T, we are writing dou V by dou T at constant P. So the equation third modifies to, just substitute these two values in the third equation. Then the equation can be written as Cp dt minus T dou V by dou T at constant P dP plus VdP is equal to 0. Next step, Cp dt can be written as T dou V by dou T at constant P minus V into dP. So our aim is, what is the concept in this Joule Kelvin effect? There arises a change in temperature. So what is the change in temperature? By seeing this equation, dt can be written as dt is equal to 1 by Cp T dou V by dou T P minus V dP. So this is this ends this Joule Kelvin effect, but this equation can be written as totally dou T by dou P. By taking this dP left side, dou T by dou P at constant H. H means enthalpy remains constant in the Joule Kelvin effect. This dou T by dou P at constant H is known as a Joule Kelvin coefficient, or sometimes this Joule Kelvin effect can be known as Joule-Thomson effect also. So this dou T by dou P at constant H is known as a Joule Kelvin coefficient, that is denoted by mu is equal to 1 by Cp T dou V by dou T at constant P minus V. This is the Joule Kelvin coefficient, that is mu. By using this equation, we can understand which gas heats up or which gas cools up when it passes through this porous plug. So by this equation, we can understand that when the gas heats up, when the gas cools up. If suppose, say, first case we are taking, if mu is negative, what is the meaning? if mu means Joule Kelvin coefficient is negative. If this is negative, the temperature increases. Because if mu is negative, dou T by dou P at constant H also negative, temperature increases. If the temperature increases, pressure also decreases. That means the gas shows a heating effect. That is simply, if mu is negative, the gas shows heating effect. Opposite to this one, if mu is positive. If mu is positive, dou T by dou P automatically positive. Then the temperature decreases. Temperature decreases, pressure as the pressure also decreases. So that means it shows cooling effect. If suppose dou T by dou P means mu is equal to 0. There is no neither cooling or nor heating. That is dou T by dou P at constant H is equal to 0. So this third point, by this third point we understand that the temperature at which the JK effect is 0 means the gas neither heats up neither cools up. The temperature is known as the inversion temperature. This inversion, depending upon this inversion temperature, the cooling effect will be more effective, like this. This is the derivation part of the Joule Kelvin coefficient. Similarly, let us calculate this Joule Kelvin effect in case of ideal gas. Means when the ideal gas is allowed to pass through the porous plug, what happens? Whether the ideal gas heats up or it cools. Let us check. Means what is the ideal gas equation? Ideal gas equation can be written as PV is equal to RT. What we need from this equation? Our equation JK effect equation is mu is depends upon the dou V by dou T at constant P. Just we have to calculate dou V by dou T at constant P from this equation. So for that purpose, V is equal to RT by P. Calculate means partially differentiate with respect to T at constant pressure. Dou V by dou T at constant P is equal to R by P. R by P can be written as V by T again. So just substitute this dou V by dou T at constant P of ideal gas in the JK coefficient equation, that is mu is equal to 1 by Cp T in place of dou V by dou T at constant P, V by T minus V is equal to 0. Here we understand that mu is equal to 0. When mu is equal to 0, what is the meaning? There is neither cooling effect nor heating effect. So that means when an ideal gas passes through the porous plug, it neither cools up nor heats up. So that is the Joule Kelvin effect for an ideal gas is 0. So that's what we are calling it as a ideal. Ideal means it neither cools up neither heats up. So this is the Joule Kelvin effect of ideal. Similarly, let us calculate the Joule Kelvin effect for van der Waals gas. Similarly, write down the van der Waals equation. After writing the van der Waals equation, just calculate dou V by dou T at constant P. So this is the method. So that is P plus A by V square, V minus B is equal to RT is the key equation of van der Waals gas for 1 mole. Similarly, differentiating this with respect to T at constant pressure, what happens? Just a UV method formula, P plus A by V square, A, B are constant here, P plus A by V square into dou V by dou T at constant P. Similarly, by keeping V minus B as a constant, V minus B into, here as a P is a constant, therefore minus 2A by v cube. Again we use this u by v method differentiating formula, 2a by v cube into dou v by dou t at constant p is equal to r. Next step, just simplifying this equation, finally we get the value of dou v by dou t at constant p. Our aim is to calculate the dou v by dou t at constant p. So p plus a by v square means in this above equation, just take dou v by dou t at constant p as a common term. The remaining term in the bracket, p plus a by v square minus v minus b into 2a by v cube into dou v by dou t by at constant p is equal to r. After that, again simplifying, that is rt minus 2a by v cube v minus b whole square is equal into dou v by dou t at constant p is equal to r into v minus b. Here we are taking some consideration here. If a constant term b is less than value, then v minus b whole square averagely equal to v square. Means we are neglecting a higher term, that is b square. And 2bv also we are neglecting comparing to v square. So the remaining, the leftover equation can be written as dou v by dou t at constant p can be written as, by simplifying this equation, r into v minus b by rt minus 2a by v. After that, again simplifying, t dou v by dou t at constant p is equal to rt into v minus b by rt minus 2a by v. Again this must be equal to v minus b by 1 minus 2a by vrt. Using binomial expansion, v minus b minus into 1 minus 2a by vrt to the power minus 1 is equal to v minus b into 1 plus 2a by vrt. v plus, again we are neglecting this 2ab by vrt term, v plus 2a by rt minus b. Just take this v left side, t dou v by dou t at constant p minus v is equal to 2a by rt minus b. This is the required, we need require this term. Means totally we calculate t left hand side LHS is equal to t dou v by dou t at constant p minus v. Just substitute this value in the JK effect equation, we get mu is equal to dou t by dou p at constant h, means mu is equal to 1 by Cp. In place of this total term t dou v by dou t at constant p minus v, we are substituting 2a by rt minus b. So this is the JK coefficient for van der Waals gas. After getting this equation, let us think over when will the gas heats up, when will the gas cools up. See here, by this equation, first case we are discussing, when 2a by rt is greater than b, what happens? That is mu will be positive. When mu will be positive, pressure difference will be negative. That is P2 must be less than P1. So dt also negative. dt negative means cooling effect. It shows the cooling effect. That is the meaning. Similarly, when 2a by rt is less than b, 2a by rt is less than b, what happens? Mu will be negative. When mu is negative, dou P negative. That is, dou P automatically negative. Then what happens to the change in temperature? Dou T will be positive. That is, dou T change in temperature will be positive means the gas heats up. That means the T 2A by RT is less than B. The gas heats up. Similarly, suppose 2A by RT is equal to B. What happens? Mu will be 0. That is, no change in temperature. Means there is the gas neither heats up neither cools up. Here one important thing is when 2A by RT is equal to B, then the temperature can be written as 2A by BR. This 2A by BR is, this temperature is known as a inversion temperature. So inversion temperature is nothing but the temperature at which the Joule Kelvin effect becomes 0. Means the gas does not show any change in its temperature. That is known as a inversion temperature. That means if the initial temperature of the gas is below the inversion temperature, what happens? It shows a cooling effect. If the initial temperature is above the inversion temperature, the gas shows heating effect on undergoing this Joule Kelvin or Joule Thomson expansion. These are the important things we understand from this Joule Kelvin effect. This is the principle and derivation of this Joule Kelvin effect. Let us again revise this one first. Here in this today's class we have understood this Joule Kelvin effect. What is the principle involved and what are the observations in this Joule Kelvin effect, derivative part of the Joule Kelvin coefficient and calculation of Joule Kelvin coefficient in case of ideal gas and van der Waals gas. Just to recall this Joule Kelvin effect, simply we define this Joule Kelvin effect as that when a gas from constant high pressure region is made to pass through the porous plug to a region of constant low pressure, it suffers a change in temperature. This is known as a Joule Kelvin effect. Sometimes this is also known as throttling process also. What is the reason here? Coming to the reason, when the gas passes through the porous plug, it has to do some work against the intermolecular forces so that its temperature decreases. To do that work, it needs some energy. That energy is taken from its own internal energy. Automatically its temperature decreases. So the main important thing of this Joule Kelvin effect is that this effect proves that the existence of the intermolecular forces of attraction among the ideal gas. Similarly, this effect is also very useful in the liquefaction of air. This is the observations. Coming to the observation, the main observation is nothing but the change in temperature. It depends upon the pressure difference on the two sides of this porous plug. After that, this is a expression for the Joule Kelvin effect. One thing again you have to remember, that is, in Joule Kelvin effect, even though there is a change in internal energy, the total energy function will be constant. That is, enthalpy function will be constant. That is, u plus pv will be constant, that is h is equal to constant. So if h is equal to constant, what is the change in enthalpy we are calculating? That is dH. H is equal to constant, dH must be 0. So this is the stepwise derivative part of the JK coefficient. This is dH change in enthalpy. After that, this equation, we are converting this equation into entropy terms. Okay. After calculating this entropy terms, simply we are calculating the change in temperature. So that is dT. So finally we get fourth equation, that is JK coefficient mu is equal to dou T by dou P at constant H is equal to 1 by Cp into T into dou V by dou T at constant P minus V. By this we understand the three cases, that is when will the gas heats up, when will be the gas cools up, when it neither shows heating or cooling. When mu is negative, it shows a heating effect. Similarly, when mu is positive, it shows a cooling effect. When mu is equal to 0, that is called JK effect will be 0. After derivating that coefficient, we calculate the JK coefficient in case of ideal gas. For the ideal gas, mu is equal to 0. That means ideal gas neither shows heating effect nor shows cooling effect when it passes through the porous plug. Coming to the van der Waals gas. For van der Waals gas, the mu can be calculated is mu is equal to 1 by Cp, final equation 1 by Cp by 2a by RT minus P. By this how we discuss the three cases depending upon 2a by RT and B. If 2a by RT is greater than B, then the gas shows cooling effect. If 2a by RT is less than B, it shows heating effect. If 2a by RT is equal to B, that is mu is equal to 0. By this, we can define the inversion temperature. Inversion temperature value is equal to T is equal to 2a by BR. This is the inversion. If this inversion temperature plays a key role in the JK effect, when the initial temperature of the gas is, if the initial temperature of the gas is below the inversion temperature, it shows a compulsory cooling effect. If the temperature above the inversion temperature, the gas exhibits a heating effect. This is the main important things you have to remember. This is about JK effect. This is the today's class. Here, depending upon this inversion temperature, firstly we talk about that hydrogen and helium, all gases shows a cooling effect except only hydrogen and helium gases. Why? Because this is the reason, because just now we have discussed about the inversion temperature and initial temperature differences. No, the initial temperature of this hydrogen and helium are above this inversion temperature, so that those two gases shows heating effect. That is the reason.